Imagine your worst nightmare from calculus class. You are asked to find the definite integral of this function. You try substitution, integration by parts, and all the other tricks in the book. Despite all your efforts, this seems impossible to find. You are at a loss how to proceed. How do we find this value? Remember that the definite integral of a function is simply the amount of area beneath the curve between two endpoints, in this case 3 and 5. That is seen here in red. It turns out that many functions cannot be integrated exactly. In such cases, we may have to resort to approximate methods to find that area. Today we are going to explore the method of Romberg integration and why it works. In short, Romberg integration takes an existing method, like the trapezoid rule, and makes improvements to the estimates for area. To see the details, we will start off with this simple function, y equals 1 over x. We want to integrate from x equals 1 to x equals 2. That is, we want to know the area beneath the curve between these 2 points. We could start off by approximating this with a trapezoid. The area is shown in pink. In this case, notice that it tends to overestimate the true area beneath the blue curve. Also notice the mesh size h equals 1. Now let's use 2 trapezoidal panels. The mesh size h equals 0.5 in this case. Notice that the area in pink is a little bit closer to the true area. With 4 trapezoidal panels, the mesh size h equals 0.25. Have you seen the pattern? Each time we double the number of panels, the mesh size gets cut in half. Also, with an increasing number of panels, the approximate area gets closer and closer to the true area. This is visually intuitive. We know from integral calculus that the exact area is equal to the natural logarithm of 2. The numerical value is seen in red. We have covered in other lessons how to compute this number in various ways, one of the best being a series expansion. You can plug the numbers into the function y equals 1 over x and use basic geometry to compute the total area for different numbers of panels. That is what I've done in this table. The area is tabulated in the 3rd column under the heading trapezoid. The 4th column is the absolute error. It is computed by subtracting the red number from each row in the 3rd column. Notice the error gets smaller as we increase the number of panels, from 4 to 128. Now to explain the 5th column. Because we double the number of panels from one row to another, it makes sense that the quotient of subsequent mesh sizes h equals 2. Consider the first 2 rows. For example, 0.25 divided by 0.125 is 2. The same applies to every other row in the table. The last column follows a similar rule to the 5th column. Instead of h, this time we divide the error in one row by the error in the next row. That gives us a ratio. This ratio isn't exactly the same from one row to another, but for the most part it is pretty close. Notice in the last row that 3.9999 is very close to 4. It is no coincidence that 4 equals 2 to the 2nd power. That is seen in green. We have seen in other lessons that the trapezoid rule is 2nd order. That is why we have the h squared, seen in green. Now let's revisit the table we just saw, except this time we are going to pretend that we don't know the exact value. This is often the case in practice. The great utility of methods like these is that we can numerically integrate functions that are otherwise difficult or impossible to integrate exactly. Notice we still double the number of panels from one row to another, and the mesh size h is cut in half each time, just like before. The area obtained from the trapezoid rule for a given number of panels is represented generically as letters A, B, C, D, E, and F. I have represented the unknown exact value as a red X. We know that the ratio of error should pretty closely equal a power of 2. That is why we see a 2 to the n in green. Remember the expression boxed in orange. We are going to consider the ratio of error from the first two rows, but the same concept applies to all the rows. For simplicity, I'm going to rewrite 2 to the n, which is a constant number, as the symbol k. Remember that the exact value of the integral x is unknown. We want to know the exact value of the integral as closely as possible, so we must solve for x. These 4 lines show the algebra to get the red x alone. Now we just have to divide both sides by 1 minus k. The final answer is boxed in orange here. This expression allows us to get a number closer to the exact value of the integral using approximations from the trapezoid rule a and b. Remember how I said that a similar analysis will give the same result for every other row in the table. So this applies for b and a, c and b, d and c, and so on. All these values are known by calculation. The ratios should all give an answer closer to the true value x. The only problem is that we don't know what k is, so we're going to have to make a few guesses. Let's start with k equals 2, seen in purple. We compute each entry in the third column using the expression on the right side of the screen. I've shown an example for rows d and c, but the same rule applies to every other row. Next, we take the average of those 5 calculations, seen in green. Next, subtract the average from each of the 5 numbers above it and take the absolute value. Those 5 differences are seen below the average. Graphically, this is what we are trying to do. Ideally, all the x values, red, should be clustered closely around a common average, the green line. So we basically want all the red bars to be the same height. The blue bars represent the absolute difference. We want these to be as close to 0 as possible. They are not, so I'm going to say that k equals 2 is not a good guess. How about k equals 3? We follow the same rules to compute each number in the third column. Notice in orange that there are 3 zeros. This is the sum of all the differences above it. Graphically, we see in red that the x values are more closely clustered around a common average, the green line. Also, the absolute differences, seen in blue, are getting closer to 0. This is a good sign, but let's keep going. How about k equals 4? We follow the same rules as before to compute each number in the third column. Notice this time in blue that there are the same number of zeros in each row of absolute difference. This indicates the calculations for x are finally clustered closely around a common average. Also notice in orange the 4 zeros underlined. Thus far, this is the minimum value we have reached for the sum. Graphically, we see that all the red bars are almost exactly aligned with the green average. Also, the absolute differences are indistinguishable from 0. This is a good sign, but let's keep going just to see what happens. What about k equals 5? Uh-oh, look at the blue. The number of zeros is not the same for each row anymore. Our calculations for x are no longer clustered closely around a common average. Also, in orange, we only have 3 zeros. Last time we had 4. The graphs show this data. The red bars are no longer in line with the green average, and the blue bars are now noticeably greater than 0. It appears we have shot past our best guess. Let's stick with k equals 4. But before moving on, I just want to point out that the first bar always tends to deviate more than the others. It is most sensitive to change. What this means in Romberg integration is that you need to use a few rows in the table, not just the first 2, in order to converge on a good answer. Once we've decided on k equals 4 in the third column, we run through the same process in the fourth column. Keep guessing k until you get calculations for x clustered closely around a common average. By trial and error, k equals 16 turned out to be the best guess. Graphically, the numbers look like this. Of course, I zoomed in from the scale on the previous charts because we are converging more closely on the exact value. In other words, our error is getting smaller. Remember what I said about the first bar? Even here it deviates most from the average. The other 3 bars are pretty close together. And again, we keep going. Into the fifth column this time. By trial and error, I stopped guessing at k equals 64. Notice in orange, the sum of differences keeps getting smaller from one column to the next. This indicates that our error is getting smaller. We are converging on the exact value. Here's the graph for that. The first bar still deviates, and now there are fewer other rows to balance out that deviation. The effect was so pronounced that I actually got better results for k equals 60. However, remember that k is a power of 2, so k equals 2 to the n. If I want an integer value of n, then k equals 64 is the best fit. If I wanted to mitigate this deviation, I could include several more rows in my table. Use 10 different panel sizes instead of 5, for example. So notice the pattern here in green. 4 equals 2 squared. 16 is 2 to the 4th. 64 is 2 to the 6th. Looks like every even integer. 2, 4, 6. That should make sense. Look in green. H to the 2, 4, 6, and 8. The first time we derived Romberg integration, we assumed that the error terms followed that pattern. In the previous table, we have shown empirically, by trial and error, that this pattern is in fact consistent with the data. It is always reassuring when two different approaches to the same problem give consistent results. But wait a minute. The first time we derived Romberg integration, we had 4s, not 2s. Is this a discrepancy? Not at all. This is easily resolved by employing laws of exponents. 2 squared is 4, so instead of 2 raised to an even integer, 2, 4, 6, 8, we get 4 raised to every positive number, 1, 2, 3, 4, etc. That can be seen on this table. 4 is 4 to the first power, 16 is 4 squared, and 64 is 4 cubed. The pattern continues. I'd say this lesson has gone on long enough. There was a lot of information to digest, but I hope I was able to explain the concept effectively. Please give me some feedback in the comment section below. To reinforce what you just learned, I highly suggest you practice for yourself. Go ahead and find the area beneath this curve using Romberg integration. Let us know what you get in the comment section below. If you enjoyed this lesson, I kindly ask that you share it with a friend, and consider subscribing to my channel so you can get notifications when new lessons are posted. I appreciate your support and look forward to seeing you again for another lesson.